So I'm pleased to introduce Andy Yu today. This talk sort of got started when I went to give a talk about our graph infrastructure at Livermore a couple months ago, and discovered that there's a lot of interesting, very large graph work going on at Livermore, and Andy agreed to come talk about what they're doing here or there. He got his PhD from Penn State a while ago. He went to Livermore and spent, I don't know, 5 years or so working on very large systems, machine systems, and then moved into the large graph area and has been doing quite a bit of work in that area since. And he's going to tell us today about some of his experiences there.
Jim. Oh, thank you all for coming to my talk. My name is Andy Yu. I am a computer scientist at Livermore National Laboratory. Probably you may be aware of this, but our lab, Livermore Lab, is known for a large scientific computation and big machines. But in the past few years, the new breed of science called data science has gained a lot of attention. This data at the lab, the data science, is pretty different from the data that used in larger scientific computation in that they are highly unstructured data, like a text, web pages, sensor data, images, and whatnot. The idea is that you want to fuse all this information from different sources into a form of graph and run graph mining algorithms to extract some useful information out of there. So our first question was that can we use those large machines we already have at the lab to run large graph algorithms? And it was kind of mixed, but the answer from our early experiment was negative. So we tried to find all the alternatives to run large graph algorithms. So I'm going to talk about the results that we gained from the series of experiments. So I'll start with a talk. Is it okay? Go ahead. Can you hear them? Can you hear me?
Will the remote sites please mute your mics, please?
Okay, so I'll start talk with the graphs that we are interested in and how they are used and some of the challenges involved in running a large graph algorithms. And one by one, I'll talk about the systems and programming models we have tested in our experiments and the results and the lessons we learned. And I'll finish the talk by sharing some of the thoughts that I have gained through this experience. Okay. So the graphs that we are interested in is called scale-free graphs, also known as Paulo graphs or complex networks. These graphs are actually random graphs that they are constructed over some period of time without any external control or of the intervention. So Barabasi and his group has shown that scale-free graphs can be constructed or built by connecting a new vertex to a popular vertices with large degrees. So this method is known as a preferential attachment. And in the preferential attachment method, if the continuous will end up having a big fat nodes with a high degree, those we call hubs. And like a Google or a Yahoo, there's a lot of connections. And the existence of these hubs actually explains a lot of known properties of scale-free graphs. For example, because because of large hubs, the degree distributions, if you plot them, they'll follow the Paulo degree distributions, meaning that there are a lot of small degree nodes, but there's a small number of very high degree vertices as well. And because of these hubs have a large connectivity, is a lot of connections to other vertices. What it does is that it actually shrink the diameter of the graph. So it may create all kind of known the properties of scale-free graph, like small diameters and the 6-degree separations, a small type of the characteristics. And also, these graphs also tend to have some kind of form of communities. And if you look at the inside of the communities, you will see some kind of self-similarities between the communities, the graph structure and overall graph structure. So the scale-free graphs are everywhere. There are a lot of them. And the most common ones are internet graphs or web graphs, or social networks like the friendship graph or citation networks. And some of the graphs are being used in bioinformatics, like a protein-protein interaction graph. Okay. So these graphs actually are usually very large, and they carries a lot of good information. So graph mining is a technique that actually you can extract this information hidden deep inside of graph. And there's a lot of uses for that. And some of the examples, the obvious one is the Google's PageRank. And this is kind of the graph algorithm that belongs to a class of problems known as spectral graph theorem, okay? And many related applications like personalized web search and random walk restart, and all that related to finding eigenvalue and eigenvector problems. Graph mining is being used in a lot of in areas of social network analysis, and the information they look for in this particular application is closely related to the structure of the graph. For example, the graph that we have is what's known as a Zachary's Karate Club graph that describes the Karate Club that exists in a US college during the 70s. And what happened to this club is that there's a feud between founding member and the coach. So eventually they split into two groups, right? By running a graph algorithms, you can actually tell which belong to which groups and who are the centers of these two groups and who are the people that work as kind of a liaison between these two groups. And graph mining, this social network analysis has many other applications. For example, you have like an in-run graph, which is very messy. But if you run proper graph mining algorithms, you can actually determine the roles of each individual, who are the secretaries, who are the CEOs, and who are the people with power. And similarly, this is what I call the center of universe problem. You may want to find a single guy in the middle who has a final word and it controls everything, like our Mr. Kenley. And similarly, you can find a people with the power, some influential people from these two guys that spending their leisure times in jail now. Also, social network analysis and graph mining getting a lot of attention from U.S. The governments, especially intelligence communities, because this can be actually a very useful tool for counterterrorism and counterintelligence. So they are getting all kinds of information from the field reports, and they fuse that information and build a graph like this. And this is actually the events graph that the person's doing what. And the running graph mining algorithms can answer questions like this: who talks to who and who does what. If you know this information, actually you can destroy the terrorist organization, or at least disrupt the operation by taking out some of the key individuals or blocking the flow of the money. And things like that. So this is a very valuable tool. And also graph mining has a lot of the commercial and academic interest. For example, we have the social networks. It is a Twitter graph, which is like a big ball of mess. And graph mining algorithms can actually dissect this kind of messy graph into a form like this. And you can answer the questions like this, who hangs out who, by dividing this group of friends, and who are the most popular dudes amongst these people. I don't know how we can make money out of this kind of information, but academic standpoint point of view, it's very interesting and fascinating to find this kind of information. And the graph mining is also used in bioinformatics. This is the protein-protein interaction graph, and there's the algorithm called community finding. And what it does is that it can find a cluster of proteins that closely, densely linked to each other. That means that, and if you know any of the functions of any of the protein, what can you tell is that these group of proteins probably do the same kind of functions. So that's how they find out. And another area of graph mining is pattern matching. In pattern matching is that you are given a pattern and you want to find all the instances of subgraph that matches this pattern. This is one example of the graph pattern matching. The pattern says that you have the two guys living in the same house, and they're monitoring and watching some factory or national monuments. And one guy rented a truck, and the other guy bought a large quantity of fertilizer. And if you find a patterns that match this kind of instance, then you may want to notify someone with law enforcement agents. And this same kind of techniques can be also used to detect frauds and to detect some scannings in cybersecurity areas for intrusion detection, like this, the bot scanning. So the problem with running large graph algorithms is that they're usually very big. I'm not sure how big of your web graphs you guys study here, but I'm sure it's more than 10 billion vertices. Ours is not as big, but it's still reaching the billion vertex graph range. The other problem in the graph mining is that the algorithms that we are interested in are usually computationally very expensive. I mean, even those running a simple graph like a breadth search on graph of this size can be very challenging. And also, many of the graph algorithms are tractable graph algorithms has the n cube or n squared type of complexity. The other lesser known problem is that the way these algorithms works, they tend to generate a lot of intermediate results. And this is the source of big performance problems. For example, this is the size of the level sets in breadth search. As you increase the levels, the size of the intermediate results shoots up very rapidly. So what are the approaches that they take to solve this problem? Government labs and the people with the resources, they use high-performance computers. And people don't, they use the relational databases or other the free source, open source the tools like how to map reduce or Dataflow systems, okay? And we evaluated all these different the platforms and programming models using different graph algorithms. But in this talk, I'll mainly focus on the graph search because this is the computationally least expensive, and that's why we were able to run the graph search in all these different platforms. Okay. The first machine system we tested is IBM. The machine called LLNL from IBM, which is a massively parallel high-performance computer. The idea is that they wanted to use a low-power, very slow processors, but lots of them. A few years back, this was the largest and fastest supercomputer in the world at the Lawrence Livermore lab. It has a 64,000 nodes. Each one has a dual cores, and it gives up 130,000 processors. And it has half a gig of memory, total of the memory, 32 terabytes of memory in total. And all the nodes are connected by a very fast 3D torus network and some tree networks. And for the programming environment, we use the message passing using MPI libraries. So how you run a graph search on BlueGene on a machine like this is very similar to what I believe the Pregel runs. So you have a graph, you chop it down into the independent sets, and you distributed all these nodes. And at the same time, you give the source of the vertex and the source of their search. Then they start reading the adjacent vertices and send out the next level sets to the proper owners of those vertices. And after receive these messages, they do the same. They find the next level sets, send out to the other vertices. And eventually, the communication pattern will become all-to-all communications. And this is very expensive type of communications until they find one guy found okay, destination is there, and then we'll send out the messages saying, stop, we are done. Okay. The problem that we found was the message size. as I shown there in earlier slides, that message volume as it actually increases. And because of that, we have a lot of problems actually making it run to a graph of the larger size. So we had to do a lot of optimizations. I'm not going to go into the details of what we did optimization, but basically what we did was that we used something called the 2D edge partitioning to reduce the number of communications. And we theoretically put the upper bounds on the message size. So they actually turned out to be great, so that we could actually save the memory space that used as a message buffer, okay? And we mapped the MPI tasks, logical processes, into a physical processor of the BlueGene in such a way that you can take advantage of fast interconnects. And we also noticed that the level sets contains a lot of redundant vertices, and we actually get rid of them before sending out to the customer. Okay, so we did a graph search on graph with 30 billion edges on BlueGene, and we did the weak scaling study. And weak scaling meaning that you increase the global program size as you increase the number of processors used. So the local program size remains constant, okay? And in this search, we randomly select a source and destination and ran it. We ran 100 of those searches and measured the average time. And as you can see, this is not, ideal weak scaling curve should remain almost flat, but this is not that bad. For the graph of this size, it took less than 5 seconds in worst case to search, okay? And what's surprising to us was that the communication time overhead, this line is very small, it's about 5%. This is not something that we expected. The reason I believe is that this is not a full shortest path and the single source shortest path type of search. It's ST type of search. You have source and destination. So the working on very small, the very small diameter graph already, so path length should be very small, like a 2. We have not seen. The path length is large enough that to see the intermediate results will go up. And also, all the optimizations we did for the communication and running on very fast network, it actually helped us with the communication time. And this work was actually first attempt to run the graph with 1 billion edges, and it was nominated as a finalist for 2005 Goldwell Award. So eliminating, I told you that there are a lot of duplicates in messages, the level sets. In worst case, 80% of the vertices were duplicates, right? So we actually, before sending out those messages, we got rid of all this duplicate message. What it did was that it's not only reduced the communication time and communication volume, but it reduced the amount of work the receiver has to do. Once the receiver receives these messages, then you have to read all the memories to go into the next level. So that's what I did. This graph shows the problems with the typical graph algorithms. We ran a random walk with restart on BlueGene for the smaller scales. And this is a log scale, the search time, and it's not really that good. It shoots up. And the reason is that it shows the communication was bottleneck. This kind of eigenvalue problems is known to be notorious to hard to scale type of problems, but well, this kind of shows that is true.
Were you using the 2D partitioning in this case as well?
Excuse me?
Were you using the?
No, we were not able to do that because we used the existing packages to run that problem, so we were not able to optimize that package. No. So the messages, the take-home message, the lessons we learned is that the programming for message passing programming is not that easy, and make it scalable was even harder. So, and as I just mentioned that, I don't think it will be useful for other graph algorithms because there are no tools or graph math packages that will scale, that will bomb out. We tried many different packages, but nothing was successful. And the other thing is that we used a random graph for in these experiments because we didn't know back then how to generate the scalable graphs fast. And random graph and scale-free graphs are really different. And I'm not sure with all this optimization that we'll scale to the very large scale-free graphs at all. And we may have to actually hack the MPI libraries for the further optimization. Okay, so the next machine that we were interested in was the shared memory multi-threading architecture, like a Craze MTA. But we did not have Cray MTA, okay? So we chose a very similar architecture called Sun Nagara, the UltraSpark T2, okay? What's special, what's interesting about this architecture is that many people know that the memory latency is bottleneck, right? So single thread, you have computation, and we wait for the memory, computation, and you wait for the memory. So in traditional of the architecture, they try to reduce this memory latency time by improving the cache utilization. In this architecture, they take it, they accept that there will be memory delays. So what they did was that instead of trying to reduce the memory latency time, they put a large number of threads and interleave this execution. So to make sure that at least one thread is running at all the time. So if you consider the computation time, you get a really good utilization of the processors. And they use the hardware actually for the context switching of the threads to reduce the overhead. So we ran a very simple benchmark, which is called RMA. The simple benchmark that basically accesses the random location of the big table in the memory. And as you can see, the more threads that we add to these benchmarks, the performance will get better. This is the beauty of the MTA architecture. Of course, it'll eventually flat out because adding more threads at a certain point will not help that much. So it was very good results. So this is how we run the graph search on Nagara. It's basically the direct translation of the message passing algorithm. You have a graph, you chop it up and assign the store into memory, and the portions of this array is assigned to threads, right? And same as the source is given to one guy, and they start reading these vertices and move on to the next the level sets. And they stored in the shared information, this dynamic information into different portions of the memory. But until the one guy says to find the destination vertex. But the problem is that this shared information is shared by many different threads. I had to use a logs. This was the problem. So this is the weak scaling study of this the graph algorithm that I just showed. And it's really bad. It's a log scale, and it improves the shoots up a lot. And the problem was that it was the log contention. We checked the hardware performance counters, and sure, as we add more threads, the idle cycling time was getting bigger and bigger. And on this particular chip, they used the software locking mechanism. So for the one single thread, I ran the code with and without the locks. The difference is about 4.5x times. So the biggest mistake we made for this one was we tried to translate the message passing algorithm on this particular architecture, and that was a mistake because of the lock contention, you cannot get the good performance out of it. And come to think of it, I think for this particular architecture, we have to develop algorithms in some asynchronous ways and try to minimize the locks. Okay, I don't know how to do it, but it has to be a different type of programming minds that require to run the algorithms on this architecture. So many people use this as a relational database because it's cheap and you can store a lot of data, right? Oops. And we chose a machine called the Netezza, which is a state-of-the-art parallel database machine to run the graph algorithms. And this machine is designed for the data warehouse type of applications. And it is kind of active disk type of approach. You push the computation to where the data is instead of pull the data out from the disk. And it uses FPGA on each data node, so the user submit the queries, it gets compiled, and portions of that query is loaded into the FPGA to expedite the query process. And also, this technique made this machine very expensive. So graph search using SQL is very simple. You start load the graph to the system, and you start with the source vertex, which is a single row table, and you expand by accessing the adjacent vertices to the next level. And from this level set, which is a bigger table, you come up with the bigger tables until you reach a table that contains the destination vertex. So how you expand the level sets in the search, like described in the yellow circle, is actually a join operation. Okay, you join the current levels, the adjacent tables, and you come up with the next level sets. So in graph algorithm,
and they're like, yeah, just doing that some more.
and the graph algorithms involves a lot of these joins. So when you run SQL code for the graph algorithms, their performance is dominated by join performance. And unfortunately, the relational databases we tried, the join performance was not that good because it was not designed to do that. The one nice thing about the relational database is you can store a large data. So just to try to test that, we ran graph search, SQL graph search, on synthetic graph with a 300 billion vertex edges. And on the paper, this was the largest graph that searched out there. I'm not sure you guys did bigger than that. But on the 672 network performance server, and then Netezza performance server at their headquarters in Massachusetts. And this is the results. They claims that 80% of the search is finished in less than 5 minutes. Okay, but there's a catch. They actually used something called a bidirectional graph search. You actually start from search from source and destination, and you move to the different directions. So what it does is that you actually cut the path length in half. So the size of the tables they have to join is pretty small. Okay, even considering that, these numbers doesn't look so good, doesn't look so impressive, and I don't think this SQL type of algorithms will scale to more general graph algorithms at all. So, I mean, relational database is easy to use and it's really cheap. But again, join performance and the join operation performance was a bottleneck, and graph involves a lot of join operations. And the other problem that we had was that we didn't have many choices for the optimizers because it's taken care of by the SQL compiler. And we didn't know what was going on behind the curtain of the SQL compilers. And their behavior is different from one compiler to another. So that was the problems we had with the relational database systems. So we asked ourselves the questions. How about we customize systems, the graph engine systems for our needs? So we have developed our own the graph search engine called MSSG, SGRACE, and MSSG is a parallel version of that. Okay, and this system is actually consists of front ends and back ends. The input to the system is the streaming edges, and we try to collect these edges into an adjacent set memory at the front ends. But eventually this memory buffer will fill out the full. So at the time we send out to the backend nodes for the storage. But because these the adjacent vertices come in as a block, as a bulk, in undetermined, unscheduled time, what we did was that we just chained these blocks of the vertices to improve actually locality. It turned out to be good. Okay. And the running of graph search algorithm is the same way as the message passing algorithm. Just difference is that we read the data from the disk instead of memory. Okay, so the strong scaling test. Strong scaling is that is a reverse of weak scaling. You fix the global program size while you're adding more number of processors. Okay. And as typical, it's pretty good number. Although the size of the graph we tried is pretty small. It's only at 10 million vertices. As we add more processors, the search time declines. But the communication overhead is actually increases. It's natural because you add more processors, that means there are more data to be exchanged. Okay. Weak scaling test is kind of interesting because I mean this is almost flat. This is not that bad for this small size graph. But what's interesting is that the overhead, disk write overhead, is actually shoots up as well as the communication overhead. And this is because you add more processors, then the overall program size gets bigger, and the more data to read and to communicate. And if you want to run graph algorithms on any of the out-of-core way, this is something that you should expect. I'll skip this.
When you say use the synthetic graph, it is still random graph or power law graph?
That was a power law graph. After the BlueGene experiments, we finally find a way to generate synthetic graph really fast. So after that experiment, everything is a synthetic scale-free graph. We learned that we tried to partition the graph so that improve the localities and reduce the communication, but it turned out to be that it was not that great. So we ended up using random partitioning, kind of round robin type of partitioning. It worked fine because many of the graph algorithms, one characteristic is that they do not have a locality. So even trying to improve the locality of the application, it's not going to work. So the message is that the lessons learned is that a well-designed custom graph engine like ours can actually outperform very expensive commercial relational data flow systems. And maybe I should show these results. This is the results of the same experiments where we ran on the Netezza machine, the relational database machine. That machine, the small rack, is actually close to $1 million. It's a very expensive machine. And of course, the size of the graph we tried is very small, but also the size of the clusters that we tried run on these experiments was 1/10 of the Netezza machine size. And in this experiment, we can finish 90% of searches in less than 90 seconds, which is pretty good. So we learned that the communication and disk writes are bottlenecks. As for the large graph algorithms, you have to take care of this one very carefully. And the one thing that we regret is that we didn't have a good programming model to start with. So it is more like the plug-in type of software development, and it took a long time to develop system. And if we had the clearly defined programming model while we're developing these products, we could have come up with a better. Okay, and I'm not sure if it may be easily applicable to the more general type of graph algorithms. It's made for the search. Okay, good. Many people are looking at the cloud computing, the MapReduce-based approach, because it's out there and it's a simple method, simple programming model, and it be able to process a lot of data in a cheap way. And I'm not going to go into details what this is because I'll appear very stupid try to explain what the MapReduce is to people at the Google. So, and our search is based on the single source shortest path method on Dijkstra's algorithm. And I'm not going into the details because you must have seen these slides a million times. Okay. So basically, what I would like to point out is that one map and reduce phase is the operation that actually goes through one level to the other. You can think of it as a one join operation in relational database SQL type of scheme, right? So you have to repeat a lot of map and reduce phases to the search. The naive implementation I just showed performed really bad because the reason is that in naive implementation, you have to actually carry out all this static and dynamic information from one phase to the other, and that's absurd. So we optimize in the way that we distributed all the static and dynamic information to vertex, all these nodes, and let the map and reduce tasks worry about their own local files and work only on that. And by doing that, we were able to get like a 3x% speed up. And even with this optimized code, we ran an actual data. It's not synthetic data called PubMed graph. Has a 30 million vertices and 5 million edges. Okay, and these are the results. Of course, the MapReduce outperform the Netezza machine, relational database machine, pretty big. I mean, this guy is actually twice as the testbed we used to run the MapReduce, but it was about 30% slower, considering the number of nodes, 30% slower than S-Grace architecture. But considering this is a MapReduce and really easy to program, this was good. However, we learned that this type of the programming model is too limited. It's better suited for embarrassingly parallel type of applications, but not necessarily the graph type applications. And I mean, it could be just the implementation issues, but this is the way of its handling this intermediate results is really bad. I mean, from one phase to the other, they have to store all these intermediate results, the level cells in a storage, and read them again. I mean, it could be just in case of the Hadoop MapReduce that we used. But that was, I mean, we are not the only ones to actually find out these problems. And a lot of people, some people in academia, they reported their problems in their papers. But this was big performance bottlenecks. So eventually, I believe this, the MapReduce will have to be evolved into some form of a data parallelism, like a data flow model. And it has to have the ability to stream the data instead of storing the intermediate results in disk and read it again. It has to have some kind of a streaming data, and coupled with the pipeline processing of this incoming data in core, in memory. Okay. Finally, we are not the only ones that recognize the problems with the data flow model. I mean, how to MapReduce model, and the people are looking at the data flow model. The Microsoft, I believe they developed something called the Dryad, and it looks like this. So I would say the data flow system is, model is the MapReduce on steroids. In a way, it is similar to MapReduce, the way how it runs, but it's more flexible and more powerful than MapReduce, because the people can freely construct their own data flow nodes, the tasks, data processing tasks, and freely construct a data flow diagram like this. Okay. And in data flow model, there are a lot of tasks called agents or the actors, and they start execution as soon as the data arrives into the inputs. And so in that way, there's no way actually you can control the flow of the data, okay? And this is a natural way to realize a data parallelism. And it turned out to be a very big factor to improve the performance was. So we happen to have a actual data flow system, running data flow system called Data Analytic Supercomputer. Is from a company called LexisNexis. So we chose this machine simply because it's available. There are not many the data flow systems out there. And this is a parallel data flow engine that runs on any commodity clusters. So in hardware-wise, there's nothing special about it, but it's actually their software that makes a lot of difference. And it has the ability to stream the data through the data flow diagrams, and they process this data in the memory in pipeline fashion. And their access to the disk is all sequentialized to reduce the arm movements, the faster disk accesses. The designer of this system actually did a really nice thing. They realized that data manipulation operation is actually only two very important operations, which is sort and join. So they optimized heck out of these two and build a system around these two constructs. One other nice thing about data flow machine compared to the relational database or MapReduce is that you have a flexibility. Users have a flexibility to construct their data management nodes in any way they want and combine them together for the better performance. And For the relational database system, we do not have. We completely rely on the SQL compiler. And in a sense, I would compare the relational database systems to the modern autofocus, auto everything kind of camera that is easy to use and does a really decent job, compared to my DOS system, which is more like my father's 1930 C3 camera, which is really painful to use. You have to control everything, dials and knobs. But if you know how to use this camera, you can still take incredible pictures. So, graph search on the DOS is very similar way to running on SQL. So you load the graph into the DOS system, but the difference is that as soon as these nodes start arriving in the DOS, they start the execution instead of waiting until all the data gets loaded. So, but the way it's implemented is still very similar to synchronous ways. So they have to create the level sets and pass to the next level, and next level. But the thing is that the other path, they don't have to wait for this to come. So the old things is running in parallel. So we ran both unidirectional and bidirectional search using actual graph, the PubMed graph, and this is the results. And for the bidirectional research, I mean, the machine size is pretty small. We ran 20 node cluster, and we were able to do search in less than 1 minute. Okay. And compared to this performance to other big data kind of systems, the DOS stands out. It's all relative to performance. The DOS system is actually 5 times better than the second best, which is S-grade system. And I contribute to this fact that we were able to, this data parallelism, were able to run the process data in parallel, and also their underlying library that optimized for sort and join and other optimizations will really work well. So combination of those two techniques, we were able to get this kind of a good performance. So there was search. We wanted to, our management wanted to actually to see how this machine can be used for more complex type of graph algorithms. So we came up with a suite of 5 graph queries, the pattern queries. This is very complex type of queries because this type of queries that generate a lot of intermediate results. It's empty-complete problem, okay, subgraph isomorphism. And that kind of large intermediate results can push the system's capability to its limit, right? So there are 5 queries, but I'm going to skip those. Okay. And we ran those 5 queries on PubMed, and these are the results we have. And looking at the query 3 and query 4, we get about the 250 and 300 speedups compared to Netezza and other relational database systems. Okay. And this particular 2 queries, the intermediate results sets are really, really big. That's the power of the Dataflow model compared to relational database model. So I personally had an experience in writing a functional programming myself, so I didn't have any problem of looking at this the graph algorithms in Dataflow way. So it was relatively easy to program for me. And the system, this model actually enables asynchronous data parallelism, and it combined with the highly optimized data manipulation constructs. And with these combinations, the performance was really good, probably the best amongst all these big data type of platforms. Okay. The thing is that hardware may be cheap, but their software was very expensive. This machine was not that cheap either. It's about comparable to Netezza machines. Okay.
How does it reconcile with your point that it's relatively easy to program?
Yeah.
Does it contradict your point, your other point?
Point of what?
Relatively easy to program?
So the software is very expensive. The library was very expensive. Yeah. Writing using, our code is written using their software constructs, but their software was very expensive. That's the point. Okay. And the other problem that we found, just like a MapReduce, because it's pure data flow model, there's no way you can actually control the flow of the data. Stop here, go there, or go there. And I found it very limiting factor, almost showstopper for this type of model to apply to the graph algorithms. We need to be, you need to have some kind of a control function mechanism embedded. So I believed in the eventual data flow model to be something like a control flow type of application, the model to be useful for graph algorithms. So this is, I got 2 slides left. Good. So this kind of summarized the experience we have. Bottom line is that no system is perfect when it, in terms of price, performance, scalability, and the ease of use. The thing is that there are 2 camps actually you can divide when it comes to large graph analysis. One is the people who wants almost real time of graph search time. For those people, they have no other options but to use very expensive one-of-kinds high-performance computers like a BlueGene or Cray MTA. So these people are usually work for government. Okay. And there are other people who care more about the cost, mostly in business and academia sectors, and the cost and the data capacity. And those people tend to stay in this, I will call it big data area. And in this region, I would give a MapReduce an edge for the price and ease of use. And when it comes to performance, I'd give edges to S-Grace and Dataflow model, right?
And nothing in the scalability at all.
I don't know. But my guess is that none of the system will scale to a large graph because, number one, as I tell you that the way this graph algorithm works, it tends to generate a lot of intermediate results. And the way this program is implemented, I believe we have to think differently. You cannot stick into looking at the Coleman's algorithm book and try to directly translate the algorithms for large graph. I don't think it's going to scale. So this is my personal gut feeling. Eventually, MapReduce model will need to be evolved into the data flow model or some kind of the workflow model with all the requirements that I mentioned earlier. And that will be ideal case in terms of when all these things can be considered. But again, another option, the very interesting option is Pregel. This is a nice option for the people running on the message page time application because it gives an ability for the users to write program very easily. I found it very interesting. And I also believe that this one can be easily extended to a shared memory type of architecture as well. There's no technical difficulties of doing that. The question is, can we push this model to this region? Model is nice, it's simple, and I don't think we have to change the model itself, but these things should have to be there to support this type of models, certain degree. Okay. So this is my final slide. I would like to share some of my thoughts. This is my personal opinion, and so it's highly subjective, but eventually, again, I believe that asynchronous data parallel model is ideal the platform and programming models to run large graph algorithms, okay, like a MapReduce or Dataflow models. And it has to be coupled with the very efficient and scalable substrate implementation to support all the streaming and pipeline processes and whatnot. So again, this is very important thing. Having said that, asynchronous data parallel model is the future. Could be wrong. Then the people that are writing a software, the algorithms, they have to think differently. And that's the thing. You have to solve this problem algorithmically. The problem, again, is that these graph algorithms use a lot of global states. And this is the source of the bottleneck. And can we really write a program without dealing with the global states? Pregel for the search, I don't think they deal with this kind of problems, right? So you have to think differently and writing a different type of algorithms. Okay. And again, the Pregel is very interesting option. I'm pretty sure, considering the fact that the Pregel is from Google, in few years, this model will dictate us. It will tell us how to write graph algorithms. And personally, I'm very interested in learning this new technology, and I'm dying to write some of the algorithms using this model. I'm sure that I'll discuss this one in meetings in the afternoon with the Sprague people here. Okay. That's it. Thank you.